Well, welcome to this section on the limit laws. I love the police officer because he's, setting the law. This section has to do with defining what are the things you're allowed to do with limits. It's kind of the things that you're going to see in the book are a little bit more of the factual kinds of stuff versus the things that we actually kind of do. But I would encourage you to take this, got a little off. I encourage you to take a minute and take a look at what's going on page 77. They have some laws in there, some rules about how limits can work. And I think if you look at them and see them, they'll kind of be intuitive and make sense to you. So take a minute, take a look at what's on page 77. That'll help you as we get into these notes. So let me kind of show you one of the things that they have in there. One of the rules is taking a limit. Now understand what a limit means. That what this is saying is as x gets closer and closer and closer to 3, what does x plus 2 get closer and closer and closer to? Now, in almost any case, when you take a limit, you can find it by substituting the number in for the variable and find out what the value is at the point. For most equations are nice, and by nice I mean they're continuous, their domain is all real numbers. And if that's the case, just what's going on at the point is what the function is doing as it gets near the point. So one of the rules that is in this section says if you have the sum of two things and you're taking the limit of it, you can break the limit of a sum apart into the sum of the limits. And so I take the first one, break it apart, take the second one, break it apart. Everywhere there's an x, you plug in 3. Now what is 2 getting close to as x gets close to 3? Now what you have to understand, when I say what is 2 getting close to, that's like saying the equation y equals 2. There's y equals 2. So as I get close to 3, what's 2 getting close to? Well, 2. It's already 2. It's forever 2. It is 2. So this could be 3, this could be 8, this could be 97. The limit of 2 as x approaches any number is going to be 2. This one's easy. Just plug in 3. And as x gets, think about that as a line, right? Y equals x. And as you get closer and closer and closer to 3, this equation is going to get closer and closer to 3. So the sum of these guys is just 5. Way more work that I just did than you need to. You should be able to just look at that and say, oh, plug in 3 and get 5. So what does this notation mean? The limit of f of x as x approaches a equals L. There's a limit. And this is true if and only if this is true. That the limit is true if and only if the limit from the left is equal to the limit from the right. This is what's called a two-sided limit. This one is a limit from the right, this one's the limit from the left. If the limit from the right is equal to the limit from the left, if they're equal to the same value, then you can say the limit exists. But it's possible for the limit from the right and the limit from the left to be equal to different numbers, and therefore the limit wouldn't exist. We'll get into that in a minute. Here's an example of what's going on. Real simple little equation. As I get closer and closer to a, and a in this case is 3. As I get closer and closer to 3, the value of this function is getting closer and closer and closer to 2. As I get closer and closer to 3 from the other side, the value of this function is getting closer and closer to 2. So if I was taking the limit of this, since the limit from the left and the limit from the right are the same thing, then I can say the limit of f of x as x approaches 3 is 2. So let's see what's going on here. This is saying, show that this limit is equal to 0. Well, for a limit to exist, the limit from the left has to equal the limit from the right. Now, because this is an absolute value, the value from the left and the value from the right are different equations. So I need to take a look at the piecewise defined function. If I pick a number greater than 0, then I get just x. If I pick a number less than 0, then the absolute value is the opposite of x. So let's see, look at the two limits. So this one's taking a look at the limit from the right. Well, if I approach 0 from the right, that means the absolute value of x is just x. And as I get closer and closer to 0, x is going to get closer and closer to 0. This one is talking about the limit from the left. Now, if I approach 0 from the left, the absolute value is going to be the opposite of x. But as it turns out, when I plug in 0 here, this value, negative x, is going to be getting closer and closer to 0 also. And since the limit from the right and the limit from the left are both equal to the same value, then I can say, therefore, by theorem 1, you wouldn't need to cite theorem 1, but therefore the limit exists. Here's another example. Let's find out what's going on here. Taking a limit. Two-sided limit doesn't have a plus or a minus. So let's look at the two sides. So as you approach this thing, this is approaching from the left. So if I approach from the left, the absolute value is the opposite of it. But now look what happens. X over x cancels and leaves -1. So as I approach from the left, this function is approaching -1. Let's take a look at what's going on from the right. As I approach from the right, then the absolute value is just x, and x over x is 1. So look at what's going on here. You've got, from the left, the function's approaching -1. As you come from the right, it's approaching +1. Therefore, the left and the right don't equal each other, so you can simply say the limit does not exist. Graphically, this is what it looks like. As I approach from the left and the right, I'm getting different values, and therefore the limit doesn't exist. So here's a little side note. I've not seen this used very often, but actually this last year on the AP, they had a question involving the squeeze theorem. So tuck this one in the back of your head. It doesn't come up often, but I have seen it. And here's the notion. Look at this blue graph. As I get closer and closer to 0, do you see how the blue graph approaches 0? And as I get closer and closer to 0 on the red graph, it also approaches 0. So if I somehow know that the graph of this black one is always in between these two, then I can say the limit as x approaches 0 of the black graph is also 0. Even if for some reason I'm not able to kind of figure out what's going on with this limit, if I know it's always in between these two, then I can say its limit is also 0. So tuck that one kind of in the back of your head. We'll try some problems off and on this year that might include that. So as I said before, when you're taking a limit, just always try to plug the number in if you can. So if I wanted to take the limit of 2x plus 5 as x approaches 3, just plug 3 into the equation, and 2 times 3 is 6, 6 plus 5 is 11. That's the limit. For nice functions, the limit is simply the function value at that point. But of course, we're going to do ones that are more interesting, which are the ones that you can't do that. But always try first. So let me show you one here and see what you think about this one. What I've got is a kind of a nasty looking expression. Find the limit as t approaches 0. Well, if I plug 0 into this equation, it's going to be undefined. So as it turns out, there's a way of dealing with this, and this is the kind of question that crops up on the multiple choice part of the exam. I'm going to multiply by the conjugate of the numerator. So back when we, early in your pre-calc year, I talked about how you never need to rationalize the denominator for me. Well, in this problem, but it's still a useful tool, and that's because to be able to do a problem like this, you have to be able to rationalize the numerator. So I'm going to rationalize this numerator by multiplying by the conjugate. The conjugate, of course, is just the opposite sign. So look what happens when you do that. You have to FOIL up top. So when you take square root of t squared plus 9 times square root of t squared plus 9, you just get t squared plus 9. The middle terms are going to cancel out, right? Negative 3 times that, positive 3 times that, they go away. And then negative 3 times 3 is negative 9. Ooh, look what happens to the 9s. They go away, and I've rationalized the numerator, leaving behind, of course, just t squared. And that cancels. Now what I've got is 1 over this. Now let's go ahead and evaluate the limit by simply plugging in 0. So when I plug in, when I plug in 0, now I get, let's see, this goes to 0. I get the square root of 9 is 3. 3 plus 3 is 6 in the denominator, and so this is 1/6. Here's what I want you to do. I want you to graph that equation on your calculator and look at values very near 0. Evaluate it at like 0.1 and then 0.01 and negative 0.1 and negative 0.01, numbers close to 0, and see if this doesn't approach the value that 1/6 is. Let me show you another kind of problem that's a little different. If I had a limit of x squared minus x minus 6 over x minus 3, limit as x approaches 3. Look at what happens. If I plug 3 into that equation, of course, it's undefined. What I'm going to do, though, with this problem then is I'm going to do some factoring. Now, anytime you do a limit problem, you always have to keep writing the limit as x approaches every single line until you take the limit. I'm going to factor the numerator, and it factors as x minus 3 and x plus 2 all over x minus 3. Aha, you say. These guys cancel out, and now I have, oops, black pen, now I have the limit as x approaches 3 of x plus 2, and now I can plug in 3 and get 5. What's happening here, of course, is there's a hole, and then when you cancel those guys out and you have the line y equals x plus 2, you have that line, let's see, y-intercept of 2, and it's going to go like this. But when it gets to 3, there's going to be a hole, and then it's going to continue on. So the limit exists even though the function's undefined at that place, because as I get closer and closer to 3, the y value is getting closer and closer to 5. I hope that helps, and let's work on a few of these and see how it goes for you.